Hi, welcome to our first video after the remote instruction kickoff. So tonight what we're going to be looking at decision trees. Decision trees are a really simple machine learning algorithm for making predictions and making inferences off of data where we have a target variable. Decision trees are very flexible and they're easy to read for humans, so they're a good place to start if you're interested in machine learning. Okay, so let's take a look at this one. What we're taking a look at the Titanic data set. So what we want to do, we want to know what's the probability of someone surviving given information about the passenger. All right, so here's how the system works. As I go down the line, if I look at it and the answer is yes or no for a particular passenger, if it's yes, I go to the left. If it's no, I go to the right. Okay, so let's go ahead. Overall, if I take a look, overall, the probability of surviving for any average passenger is 0.38, and which means that the majority of them die. That's why we say died. Now, let's go ahead and ask ourselves, what is the probability that Dr. Smith would survive on the Titanic? Okay. So, because that's what we truly care about. We truly care about making sure that I live, right? All right, so sex, male. So that's a yes. All right, so, that's bad, that's bad. The probability of dying just because I'm male drops from 0.38 to 0.13. Oh, that's not very good. All right, well, let's keep going. Now, age greater than or equal to 0.45. Okay, so if you're an older male, let's see what happens. It gets even worse. Not much worse, but it's a little bit worse. It's 0.12. Oh, that's not good. All right, so now let's think about someone else. Let's say that someone is female, and so sex male equals no, so we go to the right. Automatically, their likelihood of surviving jumps to 0.83. That's pretty good for you ladies. Now, let's take a look. Let's say that the passenger's class is third. So this is third class, first class, second class, and third class. All right, so let's go ahead and say, yeah, they're third class passenger. Let's see what happens. Oh, so a female third class passenger has a 0.67 likelihood of surviving, while a female passenger that is second or first class has a 0.96 likelihood of surviving. So if you want to survive, what you want to do, you want to be a female in the first or second class on the Titanic, if you happen to go back in time and ride on the Titanic. Now, if you want to make sure that you die, you want to be a male whose age is greater than or equal to 0.45. Or you could be a male that is younger and has a large number of siblings with them. So, that's also a high probability of dying. So if you're a male and you want to survive, you want to be young and you want to have few siblings with you. Kind of interesting. But even then, they only have a 0.78 chance of surviving. Now, you'll notice these percentages. In these percentages, they're using 100% of the data to get this 0.38. Here, 64% of the population is male, 36% is female. Down here, 62% of the data is male and age is greater than or equal to 0.45. And so we can read. So these percentages tell us how much of the data is in each one of these nodes or leaves. So you notice that this is 100%. These add up to 100. Now down here, all of these add up to 100 together. All right, that's pretty good. So what can we use decision trees for? Decision trees can be used for regression when I have a numeric target variable. In this case, we have a categorical one, a binary one of survived or died. We can use decision trees for categorical classification or survival analysis. Now, survival analysis is a situation where you don't know when a subject dies or exits the situation. So this is not a survival analysis problem, even though the problem is about survival. All right, so we can use this for predictive analytics and inference. So how does this work? What this does is it goes through and it determines the overall average of the target variable for the entire data set. Then it finds one variable to split in two. All right, so if we look back up here, what it did, it found that the single best variable for splitting was sex. And it said males this way, females that way. That was the single best way of splitting. Now down here, when it got down a little bit lower, it found that the best way to split was to go off of a numeric variable, and it had to decide what the numeric value to split on was. It decided at 4.5. So what it does, it finds a variable to split on, it computes the overall average of the target variable in the two data set splits, and then it repeats until it looks like you can't get an improvement. All right, some advantages for decision trees. It's easy to interpret for humans. You notice I'm not using a calculator, I'm not doing any computations, I'm not using algebra, I'm just reading it and I'm figuring out for the subject at hand. Humans can use these to make decisions without performing any computations. This is very good at detecting which predictors are the best predictors for the target variable. Now, something about this one. The top few variables are going to be the ones that are the most important for the target variable usually. So here, the number one that we want to consider if I was building like other models would be sex, and then age and class of their cabin. Those are the most important. We can see that number of siblings and the price of the fare are important, but not as important as these. Higher up it is, the more important it is. Now, decision trees can detect interaction between variables. So interaction, just like in the regression sense, I mean, if you see a variable in a position and so here it increases the target variable, and then down lower in the same chain, you see it again, it decreases. So if we were to have opposite results, then consider interaction for anything in between, any of the variables that appear in between. Here, this doesn't give an example of it, but this is one way to use decision trees to find interactions. This method of building models needs very little data preparation. I don't have to worry about skewness. I don't have to do box cocks. I don't have to do Johnson transformations. I don't need log transformations. I don't need any of that junk. I just need the data to run. And so if I have skewed data, it will not impact variable performance or model performance because I'm only splitting. I don't really care what the value of the split is. I just care where to split. Now, there's some disadvantages of decision trees. They can overfit pretty easily if we don't take some precautions. The predictions are relatively coarse, meaning that they don't get very precise, and that comes about by not having enough data inside those leaves at the bottom. For variable selection, it can only detect really a few variables as being really important, and it can be difficult to spot interaction with decision trees. So let's go ahead and run through the example code that I put out for us, and let's see what that looks like. So here we're using the Titanic data set. Here is how I loaded the data, and I'll put this in Canvas, so if you want to repeat this. So let's go ahead and look at the data. So I just use the head and the tail command. So here it shows just the first 6 lines. So we can see that we've got passenger ID, which isn't going to be useful for our problem. Survived, binary. 1 means they survived, 0 means they died. Passenger class, their name, that's not going to be important for us. Sex, age, sibling, spouse. So this is the number of siblings and spouses on the ship. The number of parents or children on the ship. See, there's some ticket information, their fare, their cabin, and where they embarked from. And in the document, things don't really line up very nicely, but if you run this on you run the code on your computer, the head command will look a lot better. All right, so now let's go ahead and do our data preparation. First thing I did was I went ahead and just removed the variables that I'm not going to end up using. So, and then I also reordered them. So I put target variable on the far left, then my binary category, then categorical data, ordinal data, integer data, and numeric. And this is something I like to do. I like to organize my data sets this way because it helps me remember what do I need to do when I do my data prep phase. And so we'll go ahead and take a look at what we've got in our reduced data set. So, you know, it's a lot cleaner after you get rid of some stuff. So now I look at this and I go, well, survived is 1 and died is 0. Let's go ahead and let's change this up so it's a little bit more precise. So if survived equals 1, I'm going to convert it to the word survived. If it does not equal 1, in other words, it equals 0, I'm going to change it to the word died. All right. So now let's take a look and see. So for died, we can see that 815 of the passengers died and 496 survived. All right, now I took a look at the cabin data previously before I made the video, and I saw that I had a whole bunch of, you know, like letters and numbers, and it really wasn't informative. So what I did, I went ahead and changed it to was it recorded, was it not, that's in the data set. So if I look here, we've got like less than 1,300 data points in our data total. Well, over 1,000 of them, there's no cabin information. So what I did was I changed the cabin data to indicate if the cabin is recorded in the data set. It ends up in our decision tree. It's not important, but at the time when I was doing my data prep, I didn't know this. So I went ahead and simplified this into a binary category. And so now let's take a look. All right, well, that's, you know, a little bit cleaner. Now let's take a look at the port that they embarked from. So we can see that we've got 2 missing here, 270 from port C, then from Queensland it's 123, and then from the port denoted with the S it's 914. Well, 2 is too small to be useful in this type of modeling, so I decided to go ahead and just put it in with the C group. So I converted all of the both missing values into missing or C, and if it's a C, it's converted to missing or C. So I'm binning the data. And so now here's my new embarked data set or table of data. And I went ahead and converted passenger class to ordinal factor, and I put 3, 2, 1. Because first class is, you know, the better class. Then took a look at the data, and how I have it loaded is it's current, by default it's loaded as a character variable. So to go ahead and change it into numeric, I put it into integer format. Now let's take a look. We can see that it's skewed right. So if we were doing a regular regression model that we've been talking about all semester, I would probably want to apply a log transformation or maybe a square root transformation. Remember that when I have count data, Poisson count data, the square root transform frequently will give us constant variance, which is very nice. But since I'm doing a decision tree, I don't care. I'm not going to worry about it. Now let's look at the number of parents and children that we have on board. All right, so the vast majority did not have any children or a parent with them. And I go ahead and convert it into integer data because it was loaded as character data. And I can see it's skewed once again. So if I was doing a regular regression model, I would do either log or square root transformation, but here we don't care. And all right, so now let's take a look at age. And we can see that 24 is the most common age appearing. Now, something that's interesting in the data set, if you actually go in and look, you'll see that it has decimals for some of the ages. So we take those to just be, several months old, or a few months older than the year. And we can see that we have this kind of a weird distribution. Don't really have a name for it, but it is what it is. And now, once again, we have fair. Fair has like some small decimal values floating around in it. I'm just going to convert to numeric and really not going to worry about it too much. And you can see once again it's skewed right, so I don't need to worry about it, but I could transform it. Now let's take a look at my transformed data. Things are looking a little bit more informative, easier to read. Oh hey, there's some missing values in here. Uh-oh. Gonna have to deal with that in a little bit. And then let's take a look. Let's go ahead and look at the summary statistics. I can see I've got 263 missing age values and 1 missing fair value. So what I'm going to do, I'm going to replace the missing values in age with the median age of the passengers, and then the missing value for the fare, I'm going to replace that with the median also. Now, a lot of times people want to use the mean for imputation to replace missing values, but since I got this like skewed right thing, I'm going to go ahead and use median. Since I have skewed right, I'll use median. Now, why? My personal opinion is that you should generally use the median instead of the mean if you're going to impute this way. It's just my opinion, because if it's symmetric, the median and mean are close enough to each other that doesn't matter. And if it's skewed, you should use the median. Alright, so now let's go ahead and just build the default recursive partition tree. So there's a decision tree. Here's my code for building it, and here's my code for plotting it. And it's the same one as we looked at previously. And this is with default settings. Alright, so now I'm taking a look. There's a lot of parameters to control on decision trees. So one of the issues that we can do, one of the things that we can change the number of data points we need to be able to split. So one thing that decision trees will do is they'll keep on going until there aren't very many data points in one of these nodes, and they'll stop. So if there aren't enough data points in a node, it won't split it any further. Also, if the best split results in very, very small number of data points in the resulting node or leaf, then it will go ahead and not add that to the tree as it goes through that recursive partition. So here, I set the minimum bucket to 90, or minimum split, so there has to be at least 90 data points inside a node before it splits, and there has to be at least 30 data points in the resulting subnode. And this is a complexity parameter, and we'll talk about that in a moment. So I went ahead and ran it. Now you'll notice that it's a little bit simpler. I'll look back up here. There is more stuff going on down here under with the sibling spouse split and the fare split. And we can see that things are, it's a more simple tree. It's easier to read, but honestly, the previous one's probably the better one for making predictions. But this one's easy to read, and we can see that, we can see the most important features of the model this way. Now, another thing we can do is we can increase the complexity parameter so that the tree does not get too complicated. And this will also make the tree shorter. There won't be as many splits if I do it this way. So the default is 0.1 in the R part package of R. Here we're going 0.5. The values range from 0 to 1. So when I plot that, I can see that it only split off of male-female. So this is a very simple decision tree. Not very informative, but hey, it's something. All right, now let's go in the opposite direction. Let's overfit. Why do we want to do this? This is going to be a stupid model. This is going to be a terrible model. What it's going to do, it's going to give us an idea of what would happen if we just let it go crazy and just keep on going. So what I'm going to do, I'm going to keep on splitting and splitting, and I'm not going to worry about the number of data points in a node. It can get super, super crazy, and these values we're not going to really worry about too much. Here's the max depth. That means I can have I go down a train of nodes. I can go 30 through 30 nodes all the way. All right, so let's take a look. All right, so first of all, it's giving me some warnings that there's some issues with this. Wow, look at that. Look at that. I can't even read it. It's so complicated. And it's trying to make predictions and being very, very precise. So it's going to keep on going all the way down. There's probably like hundreds, definitely hundreds of nodes down here. This is a meaningless model. This is a junk model. But you can see that up here is one extreme. This is underfitted, and this is overfitted. And this is when we do a decision tree, this is very much a Goldilocks problem. We want it just right. And that's all I got. Thank you.